Well, this is intended to be like a follow-up to my previous post where I explained a little bit about the debugger, but that was kind of rushed. And um, I think these videos are a little bit lacking in quality because I don't have as much time or I don't put in as much time as I should to get the quality out of this. But I wrote that other program that was like a little timer application, and what it was lacking was a method that converted the input of ASCII to integer. And I spent a few days not concentrating on it too much, but a little bit, and it occurred to me that one of the barriers I have in assembly is kind of imagining how to do different tasks. Like I can name the registers, but I don't really have a very good artistic feeling for it. So I just had Gemini produce this program, which does convert ASCII strings to integers. And once it produced this program and I stepped through it with the debugger and I seen how it was working, it then became very easy to understand how I would make one using the MASM macros, because for whatever reason Gemini never seems to make programs with MASM macros the way that I specify. Like I told it to use MASM macros for this program, and it did in this section, but it didn't for all the stuff down here, which it could have. But I'm actually kind of happy about that, because that gave me an opportunity to convert this into a more compact version, because this is overly verbose. So basically I took this version made by Gemini and I converted it into this, and I made one mistake, which was when I was using this load single byte, or whatever that instruction stands for. I was incrementing ESI, but I didn't realize that this instruction did that for me, and when I stepped through the debugger in it, it created a problem. Basically it made it so at some point it started reading, I guess, what you'd call arbitrary memory, and it would just mess up the numbers. Another thing that I had realized later on is where these are ASCII values here, each one of these characters is 1 byte, so this byte indicates a byte array. But right here I specified long pointer string, and that is type deft to a D word, so that wouldn't be a byte, so I shouldn't have marked this as long pointer string. But it doesn't seem to affect it any. It still works perfectly fine. But basically this program, I set it up so that it adds these two numbers, so it scans the ASCII string to an integer, and then after it does that, it has this other method which adds those two integers. So this first sum would be 511, and then this sum, which has a positive and a negative, which is also covered in this code, sums to 90. And then I have these larger numbers because what not ChatGPT, but Gemini did, it also included where what it's really doing is it's storing the counting value in EBX, and then once it's done iterating through the number, it moves EBX into EAX. But for values larger than, well, this FFFF, which is at 65,535, which would be the maximum value you could store in an 8 bit number, or an 8, yeah. So in that case, you would need both BL and BH. So this is add with carry. And when I seen ChatGPT do that, I was a little bit kind of confused, I guess, because this is part of the problem that I have with assembly. I'm not always thinking in terms of these registers and what instructions I have. Like, it wouldn't have occurred to me to use the add with carry. And I don't think it would have occurred to me to use the move 0 extends. But that's what this is. So when this runs, I'll point out some things with the stack and the base pointer, just to kind of give a little bit of insight into how stack frames work. And you'll see that. So what I also did is I wrote this batch file, this debugging batch file. So basically what this does is it sets up some path information, WinDebug there. It includes libraries, some symbol stuff, and some source path for WinDebug. And then it just kind of assembles it and links it, and then if that goes successfully, then it launches WinDebug. And in WinDebug, you can also set up workspaces, which I set up a workspace just for this called ASCII to in1, because that's just the name of the program. And so what that does is it saves the layout and the debugging breakpoints of WinDebug, because there's a lot of different windows in there. So I don't need to stay in this source file right here to show that, but so basically I can just go like this, and then D, and so here it pops up the workspace that I had set up. And so some of the things that I've customized here is, it saved my breakpoints that I have here, and looks like right here I commented out some of these numbers. So it starts off with the big numbers, but I also customized these registers, because when in debugging it, you have the these are some of the registers worth looking at, including BL and BH. Also pay attention to the ESI, which when I watched that and I had these increment ESI, which I understood what that was doing in terms of pointing at the string, but I didn't realize that this, well, actually it was this one down here, that this load string, or whatever that stands for, load string byte is what I've been thinking of it as. I didn't realize that that also incremented ESI. So when I ran this the first time, it was giving me these kind of corrupted values. So I had adjusted for that once I had seen that value change, because when these values over here change, they turn red. So I guess I might as well run the first one. And so right here you can see the call stack, and you can see, so by default WinDebug, when you run it from the command line like this, where you just put this -O and then the program, that will automatically set a breakpoint on startup. So you see that and it's doing it right here. You can see in the call stack that it's broken, that it's set at this breakpoint. So when this runs, one thing that I noticed about WinDebug is, if you have code like down here where it says call main, you can't, for some reason, there's WinDebug won't put a breakpoint in code that is not in a function, because there's no real reason why you have to put the main in a main function in assembly language, because in reality it's just pointing to a memory location and it just starts running from that point. It doesn't necessarily have to be in a function. But for some reason, well, by using the GUI, you can't set a breakpoint in any of those places. So typically you would just put your cursor on a line and then hit F9, or click on this hand right here, which sets a breakpoint. So if I do this down here, for some reason it doesn't hit that. And maybe there's a way to do it by defining the breakpoint in terms of a memory address, but I don't think that it does it in the GUI. So there's this, and so if I hit go, oh, I guess it did. I take back what I said. Okay, so it hit this call main, and so then it's gonna run this, and then it's gonna go up here. So I'll hit go again, and now it's in this ASCII to int. So last time it was part of the issue was seeing the string in the debugger. So what you can do is you can just go right here to where it has the type defined, and you can just change this to say that it's a char string, a character. I'm sorry, I misspoke. It's a pointer to a character array, which is just a string, and it's null terminated. So you see it changed it, and now it has these quotes. Well, and once I move move down further into this function, it'll populate it, and you'll see that the value will be this value right here, this 78,598. And so another interesting thing you can do in WinDebug is you can unassemble functions. So what we're seeing here is kind of like the high-level assembly that you would see, when you're coding it. But you can also see kind of the bare metal kind of assembly by using the unassemble function. So if I do that, that will also show a little bit about the stack frames and the the stack pointer and the base pointer. So this was something I was a little bit confused about for a while, but so basically there was a really old Security Now podcast where he explained what the stack is used for in terms of marking the function that you were in and marking the function that you're going into, which you can see in the debugger. That's exactly what this call stack is. So if you see right here, it says, okay, you was on line 110, and then from that you jumped into the ASCII to int function. So when the ASCII to int function gets done, it knows where to go back on line 110. But in terms of computer memory and in terms of how the processor is actually doing that with this particular calling convention, it's doing that with the base pointer and the stack pointer. So I think when this EBP push E base pointer is called, I think what that's doing is it is pushing the value of the main 110 to the stack so that it will know where to go back in the main. So my guess is that sometimes computer hacking and malware and stuff, what it could actually do is change this value so that you could return to a different memory location. And so I think that's one of the insights that you would get just by learning to program in assembly, which I'm not very good at. So if anybody has any more refined knowledge than what I'm having here, then I'm certainly open to that. Anyway, so and then it moves the stack pointer, which is the current function, into the base pointer, and then later on you'll see these values be pop back off the stack, which is what this return instruction is doing right here. So wish this thing had line numbers over here. This would be easier to connect them with line numbers. But anyway, the other thing is when you're passing arguments by the stack, then what you're really doing is you're doing that at the well, right here where it has the ESI, and that would be this instruction right here. So what it's saying is set ESI, where right here where it's saying take the pointer to the string and move it to ESI. Why it doesn't say that variable name there is because it's the base pointer plus 8, or the base pointer plus this D word, or this long pointer string. So when the stack is growing downwards, then you add to it, and when you add to it, what you're really doing is you're accessing the arguments that were passed into that stack. And when you're subtracting from it right here, what you're doing is you're accessing the local variables. So in this case, we have one that's a D word, which is this 4 here, and then there's another one. So this would be the local W result, and then this would be the local is negative as a byte. So that's 4, and then that's one more as a byte. So if this was a D word, this one would be -8, because the base pointer, I think it's been described as like an anchor, where it's kind of marking the stack frame. So the local variables are further down and the arguments are further up, and then the function is just, and then the anchor is just the actual function, which is the base pointer, which is why I guess that's why they call it the base. So that's this calling convention. There are other calling conventions which I don't know how they work exactly, but I had to stare at this for a little bit to try to figure that out. But anyway, so F9 is what do you call it? F10 is step over. So that's what I want. So I've already changed this to a char pointer, and so I guess I can't press that because it pauses my video. So I'll just click the button instead. Step over. Where are we now? Step over. Okay, so now we can see this char. We're right on this line right here, this W result, and we can see the value of this string, which is the 75,000 value. So now, as we get down through these XORs, we'll see that these values of the register all go to 0, these register values, and we'll also see that the beginning of this string variable is put in ESI, and the reason that that's put in ESI is because this load string buffer requires ESI be pointing to the string at which it manipulates. And what it's doing is it will load, and the B here is for byte. So what that will do is it'll load one character at a time into AL. And then you can see here it goes into this logic, which we'll talk about when we get to it. So step over, and right here we can see that the is negative defaults to 0. Now we're going to see ESI, that will change, and I just know from doing this before that that's going to change to 401,000. So actually it didn't change to that, and that's because I remembered I was using a different value last time. But one other interesting thing that you can do is, now that you see that this stack, that this source index pointer is pointing to this location, you can also come over here to your memory viewer, and now you can also see that value in the memory viewer. So you can see these, and then you can see these ASCII values, which 37 I think would be what? Would be 37 would be, oh, I think I have a 37 would be 7. So right here in the memory viewer we have the memory address 37, and then in ASCII it's the 7. Now if we just move this over 1 byte, change that to 13, then we kind of, what we did is we just truncated the 7, and now we see the rest of it. So not only can you see that value in the debugger right here, and it also gives the memory address right there, is if you have a problem viewing it this way. And one other thing I haven't tested yet is, right now I'm using a built-in type char to a pointer. But one of my questions, and one of the things I have to test, is if I define my own structure, if I can then put that in the type and view that the same way. I don't know if that will work or not, but it's definitely something I'd like to try at some point. I'll probably try that a little later. But yeah, you can look at the memory address, the memory values, and see that here. Continuing right along. Okay, where were we? Okay, now, oh yeah, so we're XORing EAX, EBX, and ECX so that we clear out all these things. And I have to click it because if I hit F10 it'll pause my video recorder. So I'll click that, click that, click that. Now we're on this load single byte or string byte, whatever that stands for. And that is going to put the first value in AL, and it's going to change, and it's going to increment ESI. So what it's going to do is it's going to change ESI to increment 1, so this 2 will change to a 3, and then the value that this current ESI is pointing to, it will put that in AL, and that would be so you should see AL change to a 31 because that's the memory address. So there we are. Okay, so then that changes to 31 and then increments, and now what we see is we see this high level MASM macro, which says if AL is not equal to 0, meaning 0 would be the null termination, then it's not an empty string. So if that's not the case, then continue right along. Um, I think there was, and again, you can also, like when we unassembled this function, I really wish there was a way to put line numbers in here, but again, you can see how all this stuff, the kind of the bare metal assembly, comes to life right. Well, it's kind of hard to see now. Right here, and it looks like it's also showing the branches. So this if statement is actually would be more like it's probably, I would say it must be this line right here. So that this if statement was converted into this, which is a little bit difficult. See, this is a little harder to read. But anyway, we'll see that continue right along. So right here we have this code. So if it's a signed number, if this string had a plus or a minus, which I have an example of that, and there are minuses and pluses. So not in this example. This one doesn't have that. But so step over that, and now we're seeing is AL between 0 and 9 ASCII. So and that's kind of a useful thing, because you have 0 to 9 all in one group. So basically what it's saying is, if it's one of these characters down here, or if it's one of these characters up here, then that basically means that it's an invalid alpha character. So in that case, you would just go to the next one. You could handle it some other way, but the way that I seen that not only Gemini did it, but the way that I thought might be a good way to do it is just to skip over it, which is effectively what this does. So so now we're going to put the contents of AL into ECX, and we're doing that that's just the way this logic works out. So it's also 0 extends. So what that's saying is it's saying move the value of AL, and I always have a hard time visualizing this, into ECX, but considering the fact that Intel is little Indian, which means that the most significant bits are, I think, lower in memory. I think what that means, well, I think I have a picture. Let me just see. So what that means is, okay, so ECX would be divided, so you'd have an 8-bit CL or an 8-bit AL, which would be at the end of EAX or the end of ECX, I think is the way that works out. So anyway, that always confuses me a bit, and it did confuse me in this part right here, because this number is larger than that 65,000, so a single 8-bit register is not large enough to hold the whole thing, which is when you get into this add with carry. But anyway, this is move and 0 extends. So what it's doing basically is, so it says move AL into ECX. So it's taking this AL here and moving it into ECX, which is kind of like just putting it right at the end, but the rest of these numbers are all 0. And that would be important, because if you just used a move, then I think what might happen is if there was already a value in ECX and it wasn't 0, and these higher registers outside of these last 8 bits, it would mess up the value. So I think that's why you have to use the 0 extends, because you have to 0 those out. So then you go to this one, and then what you're doing is you have the value in CL, and what you do is you just subtract the ASCII 0 from that. And so essentially what that's doing is for each, so right here, what did we have? We had a 7. So we have a 7, that's 37, and it's saying subtract 30. So if you have, well, this is hexadecimal values, but if you have hexadecimal 37 and you subtract hexadecimal 30, then you have 7, which gives us our integer value. So we'll just continue with that. And then we move the value bx into eax, and that's because as we continue down here, we'll find that ebx is the place where we're temporarily storing this number. So you'll see ebx grow into 7, then 78, then 785, and you'll see it grow, and it's doing that by manipulating these bits, and every time it needs to move over a placeholder value, it just multiplies it by 10, which is what this logic is for. So the first step of that is to move ebx into eax, and since this is our first iteration, there's nothing in ebx, so we're not going to see anything happen. We're just going to multiply 0 by 10 because we haven't moved over a placeholder, and then okay, and now, okay, so now we're going to set up ebx so that it's holding the value. So we're going to take CL, which is right here, our 7, and we're going to move that into BL, which is essentially like moving it into EBX. So there we go, that's 7, and there's nothing in BH, so we'll just keep going, and then load. Now we're going to get the next character. So the next character will be an 8, and that would be like a hex 38, I think. So you'll see ESI change, and you'll see AL change. So there we are, and so that's, and now it goes, and now it's saying until AX, AL, not AL. So until, since AL is not 0, it's a value. That means it's going to go right back up here to the repeat and do the whole thing all over again. So there we go, and we'll see it execute. There's no negatives, and it did occur to me that I could have put these negatives outside the loop, but I didn't want to. And now we'll do this one again. We're going to move AL into ECX, and there we go. You can see it over here in the debugger. Now we're going to move BX, which is what we had last time, 7. We're going to move that to AX, and then we're going to multiply AX by 10. So right here, EBX 7 from our first iteration gets moved into EAX. So there's that. And then we're going to put 10 in EBX. So 10 is hexadecimal A, and then we're going to multiply that by 10. So what we're really doing is we're moving it over a placeholder value. So it's like changing a 7 into a 70. And as we do this over and over again, it'll turn that 70 into a 70,000 as you continuously multiply the values together. But the next time it hits this multiply by 10, it will be multiplying 78 times 10. So you'd end up with 780. So there's that. And so now we have the value in EAX, which these are hexadecimal values, and I'm not sure how to show it in decimal, but I think this is correct for hexadecimal. I'm not too good at converting them in my head at this point. And then EBX, and now we load the next character, which is going to be a 5, and do the whole thing over again, and we'll step through it. Okay, and now we're going to do it again. So now we have 35, which 35 is a 5 in ASCII. So do the whole thing over again, and so now we have subtract 0 from 35, and right here in the CL, and that should change it into a 5. Okay, that changes it into a 5, and then we do the logic with converting the last value that we had, moving over the placeholder, move 10 into EBX, multiply by EBX, and then move AX into EBX, and now, so we have, you know what, let's see if I can, could I have a calculator here so I can show the conversion. Where'd my calculator go? I should have a calculator. So here we have 30C. So okay, yeah, so 30C is 780, which is what we have in EBX. And then we're going to add, so right here we're adding CL to that, and so CL is 5, so that should change the value. It would change it, let's see, that would be, yeah, so it should change EBP to 311, I think. Okay, yeah, there we go, 311. And then we're still not using this part because our number isn't that big yet. And now we're going to the next character, which is 9. And 9, do the whole thing all over again. So 9, okay, and we subtract. Now we have, so we have last time's value in EBX, and we have this current value that we're working on, this current digit in CL. We have a 9, which is the same in decimal or hex. So we converted this 9 right here. I think we might see the add with carry this time, I think. So now we're going to do it again. We're going to convert this 311. We're going to multiply that by 10 to shift over the decimal place again. So let's do that, and then multiply E B X. Okay, and that changed EAX, so now it looks like that's 1 EAA. So let's just take a look at that. 1 EAA. Okay, that's 7,850. So that's now the value of EAX, which on this current instruction we're moving EAX into EBX. Now I think we should see the add with carry. So I think when I add CL to BL, I think we'll see the carry flag populate. And this is the carry flag right here. I think this is going to turn turn true. I'm not 100% sure because no, it didn't turn true. So, but what that actually did is it added, it would have added 9 to whatever the whatever was in BL. EBX, so right now it's at, let's see, the current value would be 13B3. Well, right now, even before it executes this instruction, it's still at the right value, so this isn't going to affect it. Okay. Now we're on our last digit. Okay. Now we're on the 8, the last digit. So we'll just boom, 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 this thing again. Okay, so now we should have the final value in EBX right here, EBX. Let's just check that. EBX 13306, and that is the final value. So now we've successfully converted a string into an integer. So now what it's going to do is when it loads the next character, it's going to hit the null termination. So the null termination, and so see, now AL is 0, and so when it gets to this condition, it's going to say, oh, okay, so not 0 is true until true, then it's going to carry through. So right here, right here, right here. And earlier, when we was way up here, we said that the first character is not a negative sign, so this is negative equals 1. Well, that's going to skip over that. If it was negative, what it would do is then negate the value of EAX and turn that value into a negative, which also works. So here and here. So now we have the value in EAX right here. Okay, so turn, and now we go back down here. Okay, now we'll move the value into num1. I think what I'll do is I'll just put a breakpoint right there. And just skip. Now I'm just doing the next digit. I mean, this video is at 44 minutes, so I'm just gonna get through the rest of it. The main idea was just to show that you could change this string, and I just wanted to step through this conversion method. I'll post this code to a Git gist, and then as long as you have MASM installed, you can test all these numbers, and they all they all work fine. I mean, these small numbers, then these signed numbers, and then these large numbers, they all work fine. I have some of them commented out, but so return, and then add two integers, and then you can see it pops up here. And again, with that unassemble function, so unassemble function, how did that work exactly? So basically what you do is you put the module name, and then you put this name, so add two integers. Add two integers. So unassemble function. So this is a pretty simple method. So again, you can see that push EBP for the calling convention, then move the stack pointer to EBP. So, and then you can see again accessing the values that these two values right here, where it's saying move EAX to E base pointer plus 8 and E base pointer plus this hex value, which that, well, I don't, 0C 0, oh, that would be like 12 or something. It should be, why can't I do that? It's 10 is A, B, C, D, what is that, like 4? Well, anyway, what it's actually doing is, since the stack grows down, the base pointer is pointing at the stack, but this is adding to it and making it go back up, so it's getting these N1 val and N2 val. So that's so this is more like the raw assembly. So I mean, you would also see this if this was compiled C code. You would see the same kind of thing of this kind of stack manipulation. But anyway, so here we are. Let's just get this thing going. Go. And now we're on return. And so the total of those two added numbers would be 31591, which is, according to this, it's 202,192, which is correct. That is the sum right here. So that's correct. And now that the video is at almost 50 minutes, I'm going to pause it. But anybody who wants to play around with this code or has suggestions for how to improve it, I'll put it on a GitHub gist and put that in the link. Okay, bye-bye.